Good morning and warm welcome to our all the distinguished participants, researchers, and today's distinguished speaker, Professor Lal Mohan Saha. And today's topic is mathematics with computer applications. And before the speech, I would like to introduce Professor L.M. Saha. He has done MSc Mathematics from Patna University 1968, PhD in Applied Mathematics 1974, University of Kolkata, and Research Fellow, Scuola Normale Superiore Pisali, Italy, Postdoctorate, National Research Council, Pisa, Italy, and he has supervised 17 PhD students from Delhi University, Jamia, Chitkara, North Cape University, and he has supervised 7 students MPhil, and visiting scholar in University of Dusseldorf and University of Paderborn in Germany during 1976 and 1979, visiting professor in Japan, Ibaraki University, Kinki University, and there are many research collaborations with Professor G. Litak, Poland, Professor Munabu Yusua, Japan, Professor Yusu Tanaka, Japan, Professor E. Friswell, UK, Professor G.H. Erzai, Iran. And his research areas are nonlinear system and chaos theory, celestial mechanics, bodies with microstructure, continuum mechanics, fluid dynamics. Teaching areas where mechanics, dynamical system, numerical analysis, partial differential equations, fluid dynamics, spherical trigonometry, vectors and tensor. And he is the editor of Iranian Journal of Science and Technology, member of the editorial board of Journal of Chaos. So these are the some of the brief introduction of Professor Saha. Now I would like to I would like to request Professor V.S. Prasad to welcome Professor Saha to this morning. Thank you, sir.
Thank
now
you.
I request Professor Saha to deliver today's session. Welcome, sir.
I am thankful to Professor T.P. Sharma, the coordinator of this conference, also all distinguished guests, director of NCRT, and all other people who work for this conference. And my topic of my talk today is on mathematics and computer application. Here I will tell you a little bit about mathematics, because all you are mathematicians, you know much about mathematics. Then I will move to the geometry part, where I will tell you about fractal geometry. Then I will tell you about some modern mathematics which are now introduced in senior secondary classes. I want at least introduction part, I can say, like machine learning, artificial intelligence, etc. I will tell you, especially in machine learning, I will tell you about regression. And if I get time, I will show you how here in my computer I have Mathematica software. So I have done everything by using Mathematica. So how one can use, you can use any other software, MATLAB, maybe Python, maybe any other software. And I have obtained the results that I will show you with slides. But if I get time, I will show you by using Mathematica how you get this. Also some image recognition for the part of artificial intelligence I have done. Everything one cannot do within 1 hour, so okay. So now I am starting. So I will start with this famous quotation of Henry Poincaré, the great mathematician, and who is the father, we know him as father of chaos, you can say inventor of chaos, etc. So the quotation is, the scientist does not study nature because it is useful. He studies it because he delights in it. I like this quotation, and he delights in this in it because it is beautiful. If nature were not beautiful, it would not be worth knowing, and if nature were not worth knowing, life won't be worth living. So this is just a quotation by Henry Poincaré. Now I am coming to the mathematics. What we mean by mathematics? Mathematics, you know mathematics, but I define it like this: a logical study of shape, arrangement, and quantity, and many other related concepts. Generally, we have two types of mathematics we study: pure mathematics and applied mathematics. Applied mathematics for applications, pure mathematics to discover the principles of mathematics and to use for application on many other things. And especially this pure mathematics, again we subdivide into three parts like algebra, analysis, geometry. Algebra involves the number, about numbers and their abstraction. Analysis involves continuity and limits, and geometry is concerned with space and related concepts. Then this mathematics has contributed large, you can say, in developing world. Still it is contributing. Everything we see in this scientific world, mathematics is everywhere there. So without mathematics, nothing can be done. So these slides I have submitted there also. Then like these philosophers apply logic of mathematics to ultimate questions. Economists applied mathematics for their financial prediction, you can say. Artists use geometry, etc. So then one thing I have done here, you know very well about this concept of zero. But again, I want to repeat this. Zero is you can say, it is the identity element of addition. If someone asks, you can say zero is the identity of element. Another is, you can say zero is the cardinal number of an empty set. Zero is a number representing an empty quantity. Also you can say. And on the number line, it is in the middle, or you can say it is separating the real positive and real negatives. So here I have a mathematics tree. However, I have not drawn it. I have copied from some literature. So mathematics has, however, you can add more branches. No, these are not enough, I think. Then geometry. This is very important topic now, because geometry, which was discovered by geometry, we teach in schools. Still we are teaching in universities also. That geometry is known as Euclidean geometry. Professor Euclid, he was professor in Alexandria, Egypt, and he proposed a geometry like straight line, triangle, sphere, etc. And that geometry only speaks of regular bodies. That means which you can do, you can construct. It is not saying anything about natural bodies or natural things. So, as I have written here, it is not capable of measuring or explaining many structures like coastline, smokes, turbulent waves, snowflakes, terrain, urban pattern, etc., clouds, etc., river, snowfall, whatever we see in the nature, that geometry cannot speak anything. I mean here Euclid geometry. So it came in the mind of Mandelbrot that okay, for an artificial thing which we are constructing, Euclid geometry can speak or can give us many things. But what about the natural phenomena? What about a tree? How can we measure or explain about a tree? How can we explain about a cloud, etc.? About a mountain and many other. Whatever we see as a natural bodies, that geometry cannot speak anything. So he started thinking about the geometry which is he named as fractal geometry. So Benjamin Mandelbrot, actually he started in 1960, and he started this geometry and he named it as fractal geometry. However, fractal was known for many people before Mandelbrot also. But systematically he started this fractal geometry. Oh, this is about iteration. I'm again coming to iteration. When we say, that means it is if you have a function fx and some initial value x naught, then just to make a composition of that f of x naught. This is first iteration. f of x naught, etc. So you get first iteration. In computer, whenever we calculate anything, whenever we solve a differential equation, for example, we provide some initial value. So first iteration means whatever we get after first application, the result will be initial value for the second application. So it will continue like that. So iteration we do every time whenever we use computers. So here this is just cloud, about this turbulency, as I was telling you that Euclid geometry cannot tell us anything about this. So what we mean by fractal? Fractal is a geometrical shape. It is a geometrical shape, and it was invented by, fractal geometry was invented by Mandelbrot. And this fractal has two important properties. Two properties are fractional dimension and self-similarity. That fractals have non-integer dimension, maybe 0.5, maybe 1.7. And another is self-similar property. That means if you have a fractal, you dissect it, take a small portion, magnify, you get the original picture. Again from that, if you take a small portion, magnify, again you get the original picture. So this property is self-similarity. So fractals has two special properties, that fractal dimensions are non-integers, that means fractional, and it has self-similar property. For example, if we take in the nature, these are known, and if we take a small portion here, magnify, we get like this. Then again this shape, squared part. If we again magnify, we get like this. So this is showing self-similar property. Another here, this is just you can do by yourself. It is the logistic map. When it is a bifurcation pattern of logistic map, I have taken a small portion here. Magnified, I obtained this. Again, I have taken a small portion here. After magnification, we obtain like this. So this is showing self-similar property. Same thing we get with this Koch curve. Koch curve is modeled with coastal line. So if we take a small portion here, Koch curve I will show you. Also I will show you how we get through computer. So if we magnify this one, we get this picture. Again, a small portion of this, when you magnify, you get like. That means it is showing self-similar property. It is a fractal, and its a dimension I will tell you later on. So what we get? That there are many. You take any fractal, any natural body, and take a small portion, magnify, you may get the similar picture again and again and again. So fractals are everywhere, you can say. So why I said that fractal dimensions are non-integers. Here I am showing you. For example, take this. Take a small line. Take a line segment of unit length. Then dissect it. Divide it into n self-similar part. The self-similar is very important. That means similar. Then total length L will be, suppose you have a capital N parts, then total length will be NR, where R is the length of each part. So here it is NR, I have written it like this with red mark, NR to the power 1, because I want to say this is one dimensional. The concept is same as Hausdorff. Mandelbrot didn't change the concept. It is same concept. And this, from this, because NR, L equal to NR equal to 1, it is of unit length. So R you can find from here as 1 over N. R is called the scaling factor for this. Then let us take an area, divide it into N squares. Then area, total area A will be NR square if N are the number of squares. Where R is the, for squares, R is the length or breadth, you can say, length of any segment. So here again, I have written here NR square, with here 2, I have made it red with red color to say that it is a two-dimensional quantity. And here again scaling factor we get R equal to 1 over root over N or N to the power 1 by 2. Similarly, if you take a three-dimensional body, any volume, unit volume, every time I am taking unit volume, then if we change that volume into N cubes, that volume V can be written as NR to the power 3 equal to 1. So again I get here R, the scaling factor, as 1 over N to the power 1 over 3. Now take a unit measure of any general body. There Hausdorff, Mandelbrot has taken Hausdorff concept, and he is not violating it. Yes, dimension 1, dimension 2, dimension 3, it is okay. Now take a unit measure of any natural body. Again you divide it into n self-similar parts, capital N self-similar parts. And in each part, if there are n edges, d edges, then by same rule we can write here that the this n r to the power d equal to 1, that means here d we get log 1 over n divided by log r. Just take log both side and you get this formula, where d is the dimension of that body, that general body, you can say natural body of unit measure. So that is again, if you go back to 1, 2 dimension, 3 dimension, you are getting the same thing here. The second example, when I took an area, here you get dimension is 2. For volume, some volume Q, I obtain here dimension is 3. However, for general body, general natural object, dimension is given by log 1 over n divided by log of r. Now, this dimension is depending on n and r. Let me take an example of Cantor set. Very simple. Cantor set is a fractal. In Cantor set, what we do? We take a line, dissect into 3 parts, and we remove the middle part. And this is iteration. Continue this. Again, each line segment you divide into 3 parts, remove the middle part, etc. And continue like this, infinite time. Then you get something like points. You cannot say points. These are small line segments. And that is nothing but Cantor set. Now, what is n here? N is 2. Why? After 3 parts, we are just taking 2 parts. We are removing middle part, remaining 2 parts we consider. And however, r is 1 over 3 because every time we are dividing by 3 into 3 parts. So substitute there a value of n as 2, r as 1 over 3 in this formula, and n r to the power d equal to 1 or d equal to log 1 over r divided by r. Okay, after completing your calculation, you get dimension of Cantor set as 0.6309. Then let us come to another example like Koch curve. First you take a line. Then in the next step, you take 1/3 of that line and you form a structure like this. All these 3 lines, but however, if you join here, these 2, दिखाई पड़ रहा है नीचे? Okay. If you join this part, you get an equilateral triangle, this one. So each part is 1/3 of the original line. This was your iteration formula. If you continue for second time, you get a figure like this. For third time, you get like this. Fourth time, or after many iterations, you get a figure like this. So this is Koch curve. It is modeled with coastal line, as I told you. And its dimension here, again, n is 4 because you are keeping 4 parts every time. And r is 1 over 3 because you are dividing into 3 parts. So substituting in that formula, we get d, which is log 4 over log 3, and it is 1.261859, etc. You can approximate to 2 or 3 decimal places. Another figure here is Sierpinski triangle. You have a triangle like this. Join all middle parts of this, all lines, middle points, and remove the middle part. You get 4 triangles, middle triangle you remove. Then in the second step you get this. You continue that, you get this figure, and after many iterations you may get a triangle like this called Sierpinski. Sierpinski, he invented this. Here again r is 1 over 2 because each line you are dividing into, you are just taking the middle point. So r is 1 over 2. And how many triangles remain? Middle triangle you are removing, sir. Remaining, you have only 3 triangles remain. So dimension of this Sierpinski triangle will be log 3 over log 2, that is 1.5950. So in nature, this is just however you can say how okay, these are computer made type of things. So how we get dimension of a tree, dimension of a cabbage, dimension of a mountain, and for that there are other methods invented called these are called some like correlation dimension and what is the name that okay, there are many other ways. However, it is possible to obtain the dimension of any natural object. One thing I am telling why dimension is important. After invention of this fractal geometry and fractals, many area of science, especially medical science, improved. In whole of our body, each part of our body is nothing but fractal. Brain is a fractal. So doctors, for example, someone has a cancer in the brain. Doctor just first they identify the portion which is affected by cancer. They find the dimension of that part, and then they get the actual way for treatment, or they get some help for treatment. So these are natural fractals in this world. There are many examples you can put. I think for some of these I have written, for example, broccoli. It is not a part of like broccoli. It is 2.66, its dimension. There is another, yes, a tree has dimension 1.73. This is another computer generated fractal. So these are the thing. I can write for here many, but main thing here is the concept. Then I am passing to this part that as per the new education policy of Government of India, the suggestion is to introduce machine learning, artificial intelligence courses in schools, especially for senior secondary classes. Because if we want to move at par with all other developed nations, because in America, in Europe, you find these courses they have introduced in senior secondary classes. So here also our government has suggested. So these two courses are considered as emerging technologies today, and these two are highly mathematical. Operations are highly mathematical, and so without mathematics, no one can learn better this machine learning and artificial intelligence. So a part of this machine learning is regression. Regression is very important. What we mean by regression? You have some data set, observed data set, say, and we want to find some approximate function which is representing this data set. That means here, if you find a plot for these data sets, you get points. Now your job is to find a function which could be very similar, very nearer to these points, so that we can say approximately this function is representing this data set. So however, for linear regression, okay, when we take only one-dimensional thing like line fittings, also we say fitting of with polynomial. So you can use many software like Python, Mathematica, etc., as I told you. That this I have already told you. There is nothing new here. So regression model consists of independent variable xi, dependent variable yi, unknown parameters beta I, and error terms ei. And response function we always write like this: yi equal to some function of xi beta I plus ei. Ei is the error function. Suppose you have a set of very big set of experimental data. When you plot it, you get all these dotted points are for that. And if you want to fit this with a straight line, that is called linear regression. You have to find that straight line. However, every time you may not get a straight line only. That I am going to tell you. So here just I am showing what we mean by linear regression. You have data points, you want to find a line that will be very close to these points. So then actually you want to find like y equal to a plus bx, where a and b are. X is given, x are given points. A, your job is to find this a and b, small a and small b. Here I have written for linear regression, I have written the method. Actually this regression means here you want to minimize the error. If you have minimum error, then you get better approximation. First, I have done here whatever this theory, it is for linear regression, and anyone can copy from there. I have given it. So that to minimize, okay, we have written the error function s in this form, number 2, and then we have derived this s with respect to a, del s by del a, and then again del s by del b, and putting these two equal to 0 after manipulations, finally we obtain okay, we obtain a and b in this form as I have shown here. For example, for a small data set like 3 points, 4 points, 5 points, you can do manually, but you have a set of 100 data points, 100 experimental results. Then it is not easy to do manually. So you need computer. Okay, in this case, you have a data set 2, 3, 4, 7, 6, 5, 8, 10. Okay, so we just one by one we obtain this because in this formula you see we need sigma y, then sigma x square, sigma x, etc. So all these first we write like this. For this is x column, y column, then x square, then xy. And we have obtained all these values, sigma x, then sigma y, sigma x square, sigma xy. Substituting there, we obtained value of a as 1.5, value of b is 0.95. So the linear regression or the result of linear regression provides us the equation of the straight line as y equal to 1.5 plus 0.95x. And you see here, the original data set was like this, if you plot, because you had only 4 points. And if you put the equation of the line, you get like this. So this is just linear fit or linear regression. Regression is also known as, in computer language, we say fitting data or fit. So this is one example. However, as I told you, in nonlinear regression, actually linear, every time you may not get a straight line which is fitting or passing approximately through all the data points. You need a curve, or better to say polynomial. So this is polynomial fitting or nonlinear regression, and we actually use this least square fitting or polynomial fitting, etc. As I told you, you need computer if you have large data points. Like this one. You have here, I think 10 or 11 data points. Okay. And the linear regression, substituting for A and B, A we obtained 3.54301. No, it is B actually. And this is A. So we get Y equal to mx plus C form for this data set. It is not difficult. You can do manually also. However, I will tell you when you get large data points how to use computer. And if you plot these data, you get this curve, these points. And this straight line, fitting this straight line, you get it like this. So nearly the straight line is fitting the data points. And okay, linear regression is here, okay. Then, now let us take this case. Here you have many points. I think 30 points, maybe 30 or 31 data points. Here linear regression is providing, us y as 16.2252x plus 62.2466. And when you draw the data point and the linear regression curve, that is straight line, you get more or less this. Okay. So that here linear regression is more or less, it is okay. Now let us take this example. Here you have 11 points, example 3. And when you draw the points, you get this dotted figure. And this is the result of linear regression. And if you plot these two straight line and the points together, you get like this. So actually it is not fitting in good way. Then I didn't talk about nonlinear regression. However, the linear regression theory or the procedure you can extend to nonlinear part. However, then it will be very lengthy. However, procedure is same. You have to minimize the error. So in nonlinear regression, we obtained the fit, or you can say the approximate second degree polynomial like this, a parabola of course. And then when we fit this parabola with it is coming like this. So it is more appropriate than the linear case. However, still we are not satisfied. Then we move for third degree polynomial regression. And we obtained this third degree polynomial, and now you can see it is more or less fitting the data. So it is not that why in the beginning I told you in the definition of mathematics that it is a logical study of numbers, shapes, etc. So you need here a nonlinear regression, not linear. Nonlinear, that depends on the degree of the polynomial which will fit exactly or more or less, which will provide you minimum error. So this third degree polynomial is more or less fitting the data points. Here another example I am showing you here, this one, and linear result of linear regression, you get this line, fitting line, and if you draw the data points, you get it like that. This is just a bar chart, and if you want to fit with the linear line, it will be like this. It is so bad fitting, you can say. You cannot say that this straight line is fitting these data points. So then we move for nonlinear regression, and this is just a second degree polynomial. And now you can see it is more or less fitting the data points, because it is a parabola, and here their data points were also showing a shape of parabola. So in this way, this is another example. Here linear fit is very bad. Then we move to second degree polynomial approximation, or you can say regression. Again we find it is okay, better than first case, but not exactly. Then third degree polynomial regression I have done, and here we are getting better than the last case, but not yet appropriate, you can say. Then I move to fourth degree polynomial and I found it like this. So these are the thing. Now I wish to show you how some computer program works for this. This is just one mathematical point. The first example, we had only 4 data points. So this is, I named it data, all those 4 points that I have shown you earlier. Okay. Now list plot, let us plot these. We obtain, these are the plots of these 4, 2, 3, 4, 7, 5, 6, 5, etc. Then let us find a linear fit or linear regression, and we obtain this. This is the line y equal to 1.5 plus 0. You can put here 1y also. 1.5 plus 0.95x, and if you plot this, you get a straight line, of course. And let us fit this straight line with those data points, you get it like this. Then another case, as I told you, we have here more than so. These are the points representing the data set. I have obtained a linear fit. So, and obtained, this is the straight line for linear regression that we obtained, result of, actually it is result of linear regression. And if we plot this, we get the straight line. Then, so this is okay, nearly passing through, passing near to all these data points, and more or less it is showing okay. However, bar chart, etc. All these are operations of machine learning. In machine learning, you have to learn many things. However, here I have also shown here how to obtain a bar chart. In Mathematica, it is built in, and you need to write the appropriate command and you get the result immediately. This is another example. And result of, first I have plotted the data points, then this is the result of linear regression. You get 0. Okay, let me magnify this. So straight line will be y equal to minus 0.305753 plus 0.284701 x. And if we plot this straight line, we get it like this. And if we just plot together, then we get. So this line is not fitting exactly. So we need a linear, non-linear regression. So now let us find a second degree polynomial, and it will be, I have obtained it like this. It is y equal to or fx equal to minus 0.9723 etc. plus this is first degree term, this is second degree term. Then if we plot this, we get a curve as I was showing you there. Same example I am doing here. And if we just fit this curve, you get it like this. So this is second degree polynomial, or you can say regression, and whether it is fitting the data exactly or not, but yet we are not satisfied. So I am going for third degree. So this is third degree polynomial, and we can draw this polynomial. You get like this, and when you compare, you may get better fitting. So these are just a few more examples. This one I want to show you that these data points I have named as data list. So bar chart for this data list will be like this, and if we plot these data points, you get all these data points. Linear regression result is just this one, as I have shown you earlier also. So it is y equal to 0.237305. So this is the straight line approximated, and this is a straight line representing that polynomial, and if we compare, you get it like. So it is very bad type of, you can say, fitting. So we move for second degree polynomial regression, and we get this is second degree fx equal to whole of this, and if we plot this, we get a parabola, and when we fit, you get appropriate fitting. So this is that what I was telling, that in this way, if you have some software, if you know the how to write the code appropriately, how to do the operations. Yes, for example, if you have a data set of 1,000 data points, if you do manually, it may take 1 month for you. But here in computer, within few seconds you get the result. So this is why for modern studies we need computer. Here just I want to show you few things that okay, that like image recognition. This is a part of artificial intelligence. There is an image And we ask with this, it is Mathematica command. However, it is done on the with the theory part of artificial intelligence. We ask this with this code or this command to identify this image. So let us see whether it is identifying or not. Yes, it is. It is Amazon parrot. Then similarly, if you have, there is another image, it is identifying. Then in number line, you can show, let me. So suppose you have some two sets of real numbers, 0.7, 1.2, 2.1, then another set is 3.4, 4.5, 6.1. We want to represent these on the number line. Okay, however, with Mathematica command, it will show the these numbers. Now, the important part I am telling you now. You have this program, classify. I am saying 0. In ton, sorry, I think yes, in ton. So 0.7 represent a car in tons. 1.2 is again a car, big car, maybe big car. 2.1 is again a big car. But 3.4 ton is a truck. 4.5 is again a truck. 6.1 is. We have written this classification and asked the computer to read this. Okay, it has done it, and then this out it is coming because of artificial intelligence. Now suppose I say now see 1.6. That means classify 1.6. What will happen? There is no 1.6 here. We have not written any in this data. Nowhere you find 1.6. Now we are asking what if we have some weight of 1.6, what will be that? Then artificial intelligence will provide it is a car. It could be a car. So it is a car actually. If I write here C 5.4, there is no 5.4 here. Then it will identify it. It is a truck. So it is a truck, etc. Any other weight you put here, 4.2, there is no 4.2 there. And again, it could be, it is a truck. So it is again a truck. In this way, you put here any number, okay. This is within Mathematica code it is, but inside the working procedure is just artificial intelligence. So you get. Now, suppose I write not only this, I say express with probabilities. See 0.2. Now, in the beginning, I have written here two type of things. Two type of objects, car and truck. Car and trucks. And now I am writing here only 0.2. And I am writing here probabilities. Let us see what will happen. You find it. you find the car is probability that it is a car is 1. That means you can say surely you can say it is a car. And truck का probability है 1.58594 10 to the power minus 8. That is nearly 0. Suppose I write now here 1.6 and again I ask the same thing, then I get answer car probability that it is a car is 0.9971 and probability that it is a truck is 0.000. So this is very little number. ज़्यादा possibility है कार होने का. So these things you get. Another thing in artificial intelligence. You get it is actually inbuilt like Titanic data. So okay, we ask to read the Titanic data. It is there and artificial intelligence is showing it in its own form. That in these are the data. Age 45 year male survived. Then 38 years female survived, etc. So this is Titanic data. Now we are asking another thing that so we are asking that the missing percentage, or you can say probabilities, it is just this much. Then if we are asking that histogram Titanic data or age, so within this age and count, okay, we get this is just histogram. You can interpret. So like this you get pie chart, etc. It will provide you within pie chart that these were male people were this much, female this much, then like this survived and died, etc. All these are showing. So I think, however, these are just copied data of artificial intelligence written by Mathematica code, and we get this here, and we just, for example, here survival, etc. For that tightening that data we get, and with more detail you get the survival percentage, etc. or probabilities. So okay. I think there is no need to, we can run this one, let us see. So you get here just surviving age, etc. and these are just probabilities, you can see that. So we get this data. However, tightening data is there somewhere and used by artificial intelligence, and people have written codes in Mathematica, and in Python also you may get, and these results. So here I think I should stop, And just I have shown here that how a computer can work if you can write appropriate code, and if you have a software, very powerful software. Mathematica is very powerful because most of the researchers in the world, scientists, they are using Mathematica or MATLAB mostly. Few people are using. However, for this artificial intelligence, Python is also very important. So I should stop here. Thank you very much. If you have any question, please.
Any questions? If you have any questions, you can ask. If there is no questions, let us thank the speaker for coming this morning and delivering the talk. Although we know that this artificial intelligence, machine learnings will come because in our education system, and we'll learn more because in computer, just Sare said that all researchers, throughout the world, and we are also doing here. So with this, I thank you all on behalf of all the participants and researchers. Now, thank you, sir. And I will welcome you all for cup of tea. And after cup of tea, as usual,